Hey everyone, I'm Plaza. I work here at Software Mention, and I'm here to talk about type safety on the GPU. I'll maybe do a little bit of a hand survey. Who likes types in their JavaScript? All right, fair, nice. I guess I can do this talk now. And who previously wrote any shaders in like WebGL or WebGPU? All right, I'll have to do some explaining. That's fine. So I'm working on TypeGPU. I'm the lead developer here at Software Mention on TypeGPU. It's a type-safe toolkit for WebGPU. So to kind of, I'll explain what kind of problems the library is trying to solve, how we approach to solve those problems, our plans for the future, and any answers to the questions you may have. So why should you care about WebGPU? Well, recently it became available for React Native, so it's right now it's I guess truly cross-platform. You can use it on the web and React Native and Dino. I'm not sure about Node, but maybe. But we tried it on Dino and it worked pretty well. It's a pretty modern, low-level GPU API, which you can use for graphics as always, but you can also use it for general computing tasks. For example, performant video processing or AI inference. So I think it's a nice thing to have in your tool belt. So a simplified overview of how it kind of works. You have your JS, and you can dispatch commands, allocate resources, read from and write to memory and read from GPU memory. And you can also send just arbitrary shader code so that the GPU can process it in parallel or execute those instructions. But the API is not really designed for a type-safe language. Obviously, it's designed for JavaScript. So once you send that code, which is just a string in this case, you just send a string of instructions, which is not really type-safe. You interface with that program with numeric indices that you have to kind of remember what kind of indices you assigned to each resource. And I'll share kind of what the problems are, but the actual code that you write and you send to the GPU kind of looks like this. So yeah, this looks kind of type safe, right? You have a struct, it's called a gradient, it has fields, and you know the type, it's a vector, it's a free element vector of floats. And then you kind of say, okay, I'm expecting this to be bound from JS land, and I kind of give those numeric indices that I was talking about. And it's an array of this struct that has 32 elements. The problem is that this type safety just vanishes when we cross the boundary between WGSL, which is the language, and JavaScript. So we kind of just malloc. We just kind of create a buffer manually. We have to estimate what kind of size it has. So we have to remember, okay, this is a vector of 3 elements, but WebGPU, all the data has to be, or I guess the vectors have to be aligned to 16 bytes, at least the vector of 3 elements that are floats. So you have to have a padding of 4 bytes between, or like after the vectors, and you have to remember that. And if you don't, then the colors are going to be wrong, or depending on what you're doing. But if you're drawing a triangle, which that's like a hello world, the colors are going to be wrong, and you're not really going to know why. And you can't really console log on the GPU, so it's really hard to debug. So you have to just construct those byte buffers manually. It's not that great. So the existing solutions for that, like FreeJS, I'm pretty sure everybody's familiar and or used FreeJS before. It's a high-level abstraction, so it kind of just bypasses all of those problems, and you can do great stuff with it. You can create 3D content, you can create scenes, objects, but if you need to go down a level of abstraction, you go like really down to WebGPU or WebGL, and you just have to write those shaders. There is a new thing coming up that is TSL, which can define kind of node graphs in JS, but it's not really like imperative programming. And it's not that type safe. So the problem is, FreeJS came out before TypeScript, so it's not really designed with type safety in mind. It's hard to do that retroactively. And it is use case specific. It's geared towards graphics. So if you want to do anything else with a GPU, it's probably best to use something else. So if you're starting with a graphics thing and you want to add some AI inference, well, then you have to use another framework, and merge them together somehow, it becomes a little complicated. So yeah, that's not the best solution. Maybe we can do something better. And there's ShadeUp. You probably don't know what ShadeUp is, but we found it. It's solving the same problems that we wanted to solve with our library. And it went in the direction we were trying to go in, but then we saw this library and we talked with the author, and he kind of gave us why he would not go in the same direction as he did. Basically, he made a custom language that compiles to JS and to WGSL, so you can write the app code and the shader code, the CPU code and GPU code in the same language. So you have kind of that type safety in that code. And it's modular, so you can import from other files, but you have to learn another language, and that's a steep learning curve, and not many people want to do that. And it's hard to incorporate into existing JavaScript and WebGPU projects. So we went with a different approach. You probably know this pattern, a CSS and JS. We did something kind of similar. We did a GPU and JS. So this is the code from before. We have a struct. It's a gradient. We can do the same with our typed primitives. Just create a gradient. It's a struct. It has fields from and to with types vec3f. And then instead of using the WebGPU API, you can use the TypeGPU API and create a buffer. And instead of it being just I can go back and show you. This basically, TypeScript says it's a buffer. It has bytes in it. I don't know what's under. It doesn't even know the size of it after we create it. But in TypeGPU, we remember that. The type system remembers what kind of buffer it is. We know, okay, it's a buffer of a TypeGPU array of structs that has fields from and to vec3f, and it also can be used as a uniform. Great. Then we can use that to validate. So when we want to write to the memory, we can just pass in an array of objects, which in this case represents the struct. And then with fields from to, vec3f, vec3f, great. If we pass in a vec2f, it errors out during build time or in the IDE. Awesome. But it's still duplicated, right? Like we have it here, we have it here. So if we add another field here, we have to remember to add another field there. So it's not really that ideal. I'll show you a quick demo we have in our live examples. You can check it out after the meetup to show you that it's actually real, and then you can use it today. If I hover over the span, it does the type thing. It does the thing that I said in the slide, so I'm not lying, by the way. This works. All right, let's get back to the slides. Oh, it's still duplicated. So what do we do? Well, the best thing, I guess, to do would be to just represent everything that can be represented or written in WGSL in JS, right? Well, we're almost there. I mean, we have some stuff done. I don't know why it's black. Oh, there we go. I'll just do it again. So we did some releases. You can use the stuff that I showed. You can use the buffers. You can use the data types, and you can also use some more stuff like bind groups. But we have a lot more in the roadmap. I'm going to show kind of what we're seeing in the future, what we want it to look like. So let's say you have this WGSL. You have another binding that you can bind to in JS land, which is just a number that you can access in every function in this code. And you have a multiply function that takes in a value and returns a value, and it just multiplies those numbers together. And you have a main function, a menu entry function that you can just dispatch parallel instances of, and it runs that multiply function. Okay, so how would this look like in JS? In our APIs, you create a bind group layout with a factor and with what kind of memory space you want to put it in. This is equivalent to this uniform right here, and what kind of data type it is. And this index is kind of to enforce the code generation to say, hey, this is group 0, so if you're whenever you're referencing this with its numeric indices, it's just safer to do it this way, but you're not going to actually have to do this later on if you're just using TypeGPU without WGSL. And yeah, these numeric indices are based on the order of the fields in the object, so you don't have to do that either. And then you can take it out. You can create a multiply function. So this, I know this looks like a lot. I'll just try to slice it down into bits bit by bit. So the TypeGPU is a global object you include or import, and you can just create stuff from it. It has functions. So we call the function function. And we pass in the data types of the arguments and the return type. And this creates like a function signature, function shell that you can then implement. So we say does this. This is the implementation of it, and it's a string, but it's highlighted nicely in an IDE or like VS Code if you have the proper extension. And then you pass in what kind of dependencies it has from the outside. I know this looks like the use effect dependency array, but don't get frightened. It's not going to break your app. If you don't pass in something, it's going to tell you at runtime, hey, I'm not seeing a factor, but you used it in the code. So it's fine. It's not going to silently fail. And yeah, you do the same for main. So the cool thing about this is that these files are just normal objects, right? So you can split them around, put them in different files, in different modules, and now your code, your shader code, is automatically modular. And all you need to do to bring it back to this form so you can send it to the GPU is use the spec where we're trying to do tgpu.resolve API. You just pass in the main function, and it's going to include its definition and the definition of all of its dependencies. So that's how we do the modular thing that we wanted to do. And I guess the last piece of the puzzle, we wanted to just get rid of these strings. Because as you can see from the outside, it's type safe because you have these arguments, right? You have the return type, and the type system knows it. But inside, it's still WGSL, so it doesn't really mesh that well. But we have a working prototype. It works internally. You can implement those functions with JS or with TypeScript. And then when you access the resources from the outside, you just have the types right there. You don't have to do any code gen. You just reference the values from the outside. And our build step or just-in-time transpiler does all the translation to WGSL for you. But you have all the flexibility you want. You can create your own functions. You can access resources as you want to. You can implement the functions either in WGSL or JS, like I'm showing here. So if we forget to do anything, you can just create a function that calls some built-in stuff in WGSL, and you're fine. You don't have to eject out of TypeGPU. You still can, though. So the way this works, the way this will work, is we have a just-in-time transpiler and a build step transpiler. So in React Native, you don't actually have the body of the function at runtime. You can't toString a function and get its code because at that time it's like bytecode and it's compiled. So you have to do it as a build step. So you just install a plugin for Babel and it works fine. In Deno, you don't have a build step. You just run the TypeScript, so you have to use the JIT transpiler, so that's fine. It works too. And in Web and Node, you can just pick and choose if you're like in a code sandbox. Maybe it's easier to use the JIT transpiler instead of hooking up like a Vite plugin. Yeah, so we have that flexibility. So now that we generate WGSL from JS, right? We generate the GPU code. Can we go like backwards? Can we generate the JS from the WGSL? Yeah, I guess so, if we have like a one-to-one representation, right? So we made a package called TGPU Gen, and it's already like out. You can use it right now, but it generates the stuff that's public today. So the buffers, the data types, and the bind groups. And you can just use it like that. So if you want to migrate from a WebGPU app, you can just do that, and you have the files. You can work on them. Or if you want to use it as a code gen step, so you still want to write WGSL, but you want to have that type safety, you can just run it in the background. Anytime you change the WGSL, it recreates the JS. So let's go through some example use cases of how you can incorporate TypeGPU into your workflow. So let's say, okay, I want to use TypeGPU in my existing WebGPU project. We'll cover that. I want to call some utility function, like that's from another module, from my shaders without a full migration to TypeGPU, which is also fair. And the third one is I just want to create a fully type-safe GPU program from the start. I don't have anything written yet, so I just want to start with TypeGPU. Okay. So the first use case, we can just, if we have a shader.wgsl, which is a file with the shader code in it, we can run npx tgpu gen, generate the equivalent JS for it. and still use the shader code underneath, but when we interface with the program after it's already been dispatched, you can just use the generated JS primitives. So you can import the shader code as you used to, and then import the gradient struct, for example, and create the buffer as I showed in the beginning. For the second approach, if you want to call some utility function, well, you can't really use the original shader code because the function may have additional dependencies, some other functions that it uses underneath. So it's best to let us recreate the code for you. So instead of using shader WGSL as you used to, you use whatever was generated during that code gen step. For example, one of the things that was generated is the entry function. So for example, a fragment shader that works on every pixel in parallel. You can just say that, okay, we're going to link an external function from some other module and then resolve that function, and we get the whole code back as we would with all the additional dependencies that the external module needs. So that's nice. It's pretty simple to do. And finally, if we don't have an existing WGSL shader, we can just write in the JS thing that I showed. So you can just write imperative code with all the ifs, fors, whiles you want. Just don't do an infinite loop on the GPU. It's not nice. You have to restart your whole computer. No, don't do that. But yeah, you can just do a purple screen. You can create a type pipeline, and everything just works nicely. And you don't have to learn another language. You can just do it in TypeScript. So I guess our approach, as opposed to other libraries, is we're not really use case specific. So we're not coming out and providing GPU a GPU implementation for a specific use case like graphics or AI. We're basically just providing a very tiny layer on top of WebGPU that is type safe, and you can pull in from other modules that we're also planning to create, like a module for AI inference or generating noise, or just general basic shapes that you can draw, and more complex modules we think are going to rise out of that, or either we're going to create them or we hope people create them as well. And in that way, you don't have to include a whole bundle of a framework. You just include the core, which we want to keep very minimal, and any module that extends the functionality as much as you need. If you start with like an AI app, and you want to do some rendering, you can just install the module that does the rendering. Yeah, we're really excited about this, and I hope, I hope TypeGPU makes GPU programming a little bit less scary, so that you don't have to learn a new language. Please give us a star. We're on GitHub. We have a Discord, so you can join us there and talk to us about GPU programming if you have any questions about that. And yeah, thanks a lot. If you have any questions, you can do it now or later.
Just to be really close to your mouth. Thank you for your presentation. So my question is, I was never working with such a technology in either WebGPU or WebGL. So my basic question is, what is the most common business purpose to use this technology? Is it for online gaming or just for my interest? What is
it? Yeah, of course. I mean, the GPU was originally used for graphics. So if you want to do high performance graphics that is custom, so you want to do some simulation, some fluid simulation on your native app or on the web. I think that's the best way to do it in a performant way. I think it can be used as a way to stand out from other apps. If you use existing solutions, it can look a little bit samey. So if you want to show that prowess, you can use a custom shader, and we hope that it's going to become a little simpler to do it with our solution. But just any algorithm that can be computed in parallel, I think, can benefit from running on a GPU. Like I said, AI inference. So that's becoming a boom right now. So yeah, a lot of things, but things that can run in parallel on graphics, basically.
Okay, thank you.